once again single equation, tau is equal to Fa y bar by Ib, where A y bar is equal to moment of the area about neutral axis. Very interesting point. A y bar meaning is remaining unchanged, moment of the area about neutral axis. Now at the neutral axis, the I section divide into two parts, the top rectangle and sum of the portion of the web. So we have to compute the area for both the portion, and then we have to multiply by the distance of the CG from that area to the neutral axis. So let us compute this one over here right now on this PPT. So if you refer the figure, then it is nothing but the moment of the area of the upper flange about neutral axis plus moment of the area of the web about neutral axis. So let us refer these things over here on this tabletop. I section. This is our neutral axis. Now the area under consideration is this one value, because our intention is to find out the variation of shear stress at neutral axis. So whatever the area above the neutral axis, we have to compute it over here right now. So this depth, which is known to us 133.49, thickness of the flange is known to us, 200 is the width of a flange, and thickness of web is of 50 mm. So if we will divide into two parts, the one and the second, then A y bar is equal to, for the first part is nothing but the area 200 multiplied by 50 multiply by y bar for the first area is the CG over here, then 133.49 minus 50 by 2 plus another area, that is 133.49 minus 50 available thickness, available length for a web, minus 50 multiply by thickness 50. This will become the area of this shaded figure, this area, multiply by the y bar distance, that is nothing but this 133.49 minus 50 divide by 2. CG is over here. This distance available with us is 133.49 minus 50. So CG is at the center, half of the distance, we have to compute it for y bar. The same thing which has been taken on this PPT, please understood on this, come on this PPT. So now by solving this, we achieve A y bar is equal to 1259164.5 value of A y bar in terms of millimeter raised to 3. Now B is equal to 50 mm, available width at neutral axis for a section is 50 mm. So tau max is equal to Fa y bar by Ib, by value putting F is equal to 50,000, A y bar value which is known to us, I which is known to us, B is 50 mm, we got it as 4.42 Newton per mm square, that is megapascal, which is obviously maximum value noted at the neutral axis, 4.42 Newton per mm square. Next step, the flange, the shear stress in the lower flange just at the junction of the lower flange and the web, which is given by tau is equal to Fa y bar by Ib, fundamental equation, where A y bar is equal to moment of the area of the lower flange about neutral axis, that is the area of the lower flange 130 into 50 multiply by y bar, that is distance of the CG of the bottom flange to the neutral axis, that is 166.51 minus 25. If you want to understood over here, then please come on this tabletop. This is my I axis, intention is to find out the variation at the junction. Area under consideration is this one. Area 130 into 50. CG distance is this one, that is 166.51 minus 50 by 2. So the same thing which has been adopted over here, and B, please on this PPT, B is equal to 130 mm, width available at the junction of web and the flange, that is 130 mm. It is this one. B is the width of the flange, and by putting the value tau is equal to Fa y bar by Ib, where F is equal to 50,000 Newton, A y bar which we have already been computed 918125 divided by Ib, we obtain the answer 1.24 Newton per mm square. This is the variation at the junction from flange to web. Now the shear stress in the web just at the junction of the web and the lower flange will be suddenly increases from 1.24 Newton per mm square to the width of flange to the width of web, that is 130 divided by 50 multiplied by the computed value of tau. So if you refer this figure and PPT both, then you will see that it is 1.24 into 130 divided by 50, we got it 3.22 Newton per mm square. So by using all this value, we can compute the shear stress distribution diagram as follows. Starting from the top and bottom flanges, at the extreme fibers, the value of the stresses are 0. As we proceed or we go for the variation from this top fiber to the bottom fiber of a flanges, the variation is of parabolic nature, and we got it 0.95. Then the shear stress value suddenly increases from 0.95 to 3.8 Newton per mm square. At neutral axis, we got it the maximum value of the shear stress, that is of 4.42 Newton per mm square, while at the bottom edge of the flange is 0, while junction between the flange and the web, the variation is of 1.23 Newton per mm square, while at the same junction the web will take care the shear stress value is of 3.22 Newton per mm square. So likewise, from this way we can compute the shear stresses, we can plot the shear stress distribution diagram. Let us proceed further for the triangular section. Now, right now we have studied the variation of shear stress distribution diagram for rectangular section, circular section, T section, I section, unsymmetrical sections. Now we proceed further for the triangular section, and let us be noted down how the variation of shear stress will be taken care for triangular section. Please refer on the PPT. Find the shear stress distribution diagram for a triangular section having a base B and altitude h. The beam is placed with its base horizontal. The shear force acting on a beam at a section is capital F. Please refer the data, try to plot the figure, and what question which has been asked will be understood better way. This is the given data. Base B, altitude h. The neutral axis of the triangle ABC will be lie at the CG of the triangle, and the CG of the triangle will be at a distance of 2h by 3 from the top or h by 3 from the bottom. So in case of a triangular section need not to be calculated the CJ, we know the formula hence. So 2h by 3 from the top is the distance. Now consider a level EF at a distance y from the neutral axis. The shear stress at this level is given by FA y bar by IB. So please refer the figure. Intention is to find out the variation of the shear stress along a section of a triangle. We want to derive an equation. To derive an equation, let us take a one simple single strip EF at distance y from neutral axis, and our intention is to find out the variation of shear stress at this layer EF. So we have to take the area above this layer EF, that is we have to take the area of triangle CEF, and then we have to take the CG of that triangle. From that CG to the neutral axis we can find out the y bar. So A and y bar we can find out. Likewise that F value which has been given to us, that is F itself. I is the moment of inertia of this triangle about neutral axis, and B is the base width at the layer EF, because our intention is to find out the variation of shear stress at layer EF. So now AY bar, that is the moment of the shaded area about a neutral axis, which is equal to area of triangle, small triangle CEF multiply by distance of the CG of the triangle CEF from neutral axis. We know the area of a small triangle, shaded portion of triangle CEF is equal to half into width multiply by x. Please refer this one figure. Assuming the available height from the apex to the EF is x, so area is equal to half into base into height, half into EF into x, multiply by the distance y bar, that is 2h by 3 minus 2x by 3. Please refer it carefully. 2h by 3 is available from this, minus 2x by 3, that is from C to CG distance, that is available from the CG to the apex. So remaining one is 2h by 3 minus 2x by 3 is our y bar value. Now we know the triangle CEF and CAB are similar triangle. CEF and CAB are similar triangle. So refer the figure. This CAB and CEF both are the similar triangle, and hence ratio of EF by AB, that is base width for triangle CEF divided by base width of triangle CAB, is equal to x by h. That means we can write down EF is equal to x by h into AB. AB, the value which is known to us, that is B. Hence EF is equal to xb by h. So by putting the value of EF in the equation of AY bar over here, we can get an equation half of xh by bx by h into x multiply by 2/3, which is out of the bracket, we got it x minus h. So once again simplifying this, we can achieve an equation AY bar is equal to 1/3 into bx square by h bracket h minus x. Next, I, that is the moment of inertia of the whole triangular section CAB about neutral axis. We will keep the term I as it is. We are not putting the value I in terms of the B as well as H. Let I is remaining same. B, that is the actual width at the level EF, that is the value EF itself is equal to Bx by H. By putting all this value in our equation, tau is equal to Fa y bar by Ib. F is nothing but F, I is also I. Only we have to replace the value of A y bar as 1/3 of B x square by H bracket H minus X divide by B, that is Xb by H. By simplifying this, we got tau is equal to F by 3I bracket Hx minus X square. Please refer and told this equation number 1. Refer it out over here that tau is proportional with the minus x square term. X square term suggests that the variation is in terms of the parabolic nature. Minus term suggests that as we proceed from neutral axis to the top, the value of shear stress goes reducing. So, from this equation number 1, it is clear that the variation of tau with respect to x is parabolic nature. At the top, x is equal to 0. That value of tau is equal to 0 because we have to replace y is equal to x. In that case, the bracketed term will become 0 and hence the value of tau is become 0. Also at the bottom, x is equal to h, the tau is equal to 0. At the neutral axis, x is equal to 2h by 3, and let us we replace the value of x is equal to 2h by 3 in our simple single equation. Tau is equal to f over 3I bracket h into 2h by 3 minus, instead of x we have to put 2h by 3 whole square. By simplifying this, we got f by 3I bracket 2h square by 3 minus 4h square by 9, and we got the tau is equal to 2 by 27 f h square by I. Now h